Okay. So this Z is square root of R square plus X minus X square, and RS does not depend on frequency. It's constant. If it is 50 ohms, it's 50 ohms, independent of the frequency of the voltage source. But XC, which is 1 by omega C, as the frequency increases, the value of XC will decrease, and XL will increase as frequency increases. So it is possible that for one particular frequency, XC and XL will be same. Okay, let the frequency be omega naught, so that at that particular frequency, X is 1 by omega naught C and XL is omega naught L. And if they are equal, then the frequency should have this value, 1 by root LC. So at this particular frequency, this will disappear. X minus XL becomes 0. So the current will become Vm by R. And since this denominator, this is positive, and this second term is also positive, and V is constant, Vm is constant. So as frequency changes, only this will change. So we'll get the maximum value of current when this X minus XL is 0. That happens at the resonance frequency omega naught. So this particular frequency, Z is minimum and the current is maximum. So the current amplitude is maximum, okay, at resonance frequency. Okay, so given the value of L and C, okay, the resonance frequency is known. So it depends on the value of L and C. So RLC series circuit. And what is wattless current? Any idea? Wattless current. The current which does not produce any power. What is unit of power? So wattless current means the current which does not have any power dissipation. So power, the current in pure inductor and pure capacitor are wattless currents, because power in a inductor and capacitor is 0, right? Average power in an inductor, here the average power is 0, right? Power is the blue curve, which is sine theta and sine omega t cos omega t. So average power in inductor and capacitor is 0. So the current inductor and capacitor is wattless current, because power dissipation due to that current is 0. But for a resistor, the current and voltage are in the same phase, so that will have a dissipation. So this current is called watt current, or the other current is called wattless current. Okay, so the current flowing in a pure inductor and pure capacitor is wattless current. RMS value of sign variation. That's a basic definition. If you have a sign variation like this, the sine omega t. If you look at the definition, the RMS values RMS, right? So to first square it, so to square sine, and then we take the mean, that is average, and then we take the square root. Okay, so this will turn out to be, over this value is say Im. So this will turn out to be Im by root 2. So this value is called IRMS, okay, which is 0.707 is the peak value. So this is how the RMS value is defined. Yeah, I think just put both. Okay, this is average value of a function. This actually I did in class, the RMS value. Suppose I can also take anything voltage also. So V is say Vm into sine omega t. I have to find RMS value of the voltage. So to get that, first RMS, right? First I have to square it. So I have to Vm square sine square omega t. And then I have to take the mean, that is average of this one. Okay, and then I take the square root. Vm square, Vm is a constant, so Vm square will come out. So average of sine square omega t, average of sine square omega t is half. Okay, this is a standard result. And then I will take the square root to get the RMS value. So VRMS is square root of this one, that is square root of Vm square into 1 by 2. So it is Vm by root 2. Okay. This average is time average. So average of sine square omega t, it's 2 because average of sine square, one way of getting this result is average of sine square omega t time average is same as average of cos square omega t, because sine and cos are nothing but the same waveform with a phase difference. So in one period, this is the sine and cos will look like this. So average of sine and cos are same, time average. So average of sine square and cos square also same. And we know that sine square plus cos square is 1. So from this I get the average of sine square as half of average of 1, which is 1. So it is half. So that's one way of getting the result that average of sine square is half. Okay, so the basic thing I want to convey is the RMS value is related to peak value as 1 by root 2. So you have some variation with respect to time. It can be voltage or current. And this is the peak value. See, this is the voltage, the Vm. So the RMS value is 0.7 times this VRMS is 0.70 times the peak value, which is Vm by root 2. So RMS value of sine variation is 1 by root 2 of the peak value, which is 0.07 times the peak value. And what is power factor? Power factor. Suppose this is an electrical device which has got impedance Z. Because it's not a pure resistor, it's combination of resistor and inductor and capacitor will have a Z value. And this is the current I. So the power in this dissipated by this impedance is V into I. Right? For a resistor it's also same I, but for impedance will V into I. But this V and I are RMS values. So I can write as V RMS into I RMS. But for an inductor, we know this power is 0, right? And for a pure capacitor, the power is 0. So it's actually V into I into cos phi, where phi is the phase difference between the voltage and the current phases. So for a pure inductor, this will be either 90 or plus 10 or minus 90. And for a capacitor will be again plus 10 or minus 90. But for a resistance, the phi will be 0. So this phi is called, actually cos phi is called the, what is it called? Power factor. Okay, cos phi. power in AC circuit. VMI, right? Okay, in general, see, for a circuit which has got both L and C, the angle between the voltage and current will be phi, which is given as this one, tan inverse XC minus XL by R. So in pure resistive circuit, okay, the voltage phasor and the current phasor are in the same direction. Okay, for a pure capacitor, current will lead. So current is here. So this is current I, this is voltage, and this is leading by 90 degrees. For an inductor, the current will lag. So this is voltage, means the current will be here. Okay, but for a combination of R, L, and C, depending on what is dominating, suppose the voltage is this one, the current which is flowing that combination will be at an angle phi. Okay, that phi angle is given by this is R, this combination of XL and XC, XL minus XC. So this angle phi is tan inverse XL minus XC by R, or I can say tan phi is XL minus XC by R. Okay, so the power dissipated by this combination, which has got power dissipated, this resistance is V into I. By this pure capacitor is 0. By this pure inductor is 0. But you have a combination, then voltage and current will be at a phase difference of 5 degrees. So in this case, the power will be V into I into cos phi. So this you can apply for a pure resistive circuit where phi is 0. So if you put phi equal to 0, you get the power as V into I. For a pure capacitor, phi is 90 degrees. You can weigh plus 90 minus 90. So if you put that one, you'll get this one. And for a pure inductor, so phi is 90 degrees. If you put, get this value as 0. But for a combination of R and C, phi will have some value, and tan phi is given as XL minus XC by R. So in that case, power dissipated is V into I into cos phi. So this cos phi is called power factor. So for a RLC combination circuit, power is V into I, which is Vm sine omega t, and current will have a phase difference of phi with the voltage. For a pure resistor, is phi is 0. For pure inductor is 90 plus or minus 90. We have to figure that out. And for capacitors is plus or minus 90. But for a combination of R and C, it will be different from 90 degrees. And that angle is given by this triangle. This triangle, R and XC minus XL combination. So from this triangle, we get this value of phi. So phi basically depends on how this value of XC minus XL can compare to R. Okay, so once I know this phi, I can get the power dissipated the RLC combination. Okay, so in terms of time variation, we can write like this. If you combine this, finally you get this result. V equal to I into I, power is V into I into cos phi, where this V is RMS value. V RMS, I RMS, and phi is the angle between voltage and current. Okay, so this also I can write as I square Z or V square by Z. And this cos phi is called power factor. So he has taken resistive circuit. In that case, phi is 0. Okay, it's just I square into Z, and Z will become R for a pure resistive circuit. Pure inductor or capacitive circuit, cos phi is 0. Okay, that is called wattless current. I mentioned, right, sometime back. Okay, this for pure inductor and capacitor. Only that we have the current which is wattless. But for a combination, this phi is in between 0 and 90 degrees. And that is given by tan phi equal to XC minus XL by R. Under resonance condition, XC and XL will go away. It's like a pure resistive circuit at resonance condition. At resonance, the Z will become a pure resistance. Then it will become I square R. Okay. Ampere circuit law we already know, right? This is done in 4th chapter. And what is it used for? Anyone? Ampere's second law gives basically the magnetic field, and the source is current, right? Like Gauss law of electrostatics gives me electric field to the source, which is a charge present inside. So here this Ampere's second law gives me integral B dot dl over this closed contour equal to mu naught into I. This is Ampere's second law. Okay, so this is basically used to find magnetic field given the source, which is the current I. It's used for finding the magnetic field given the current. Electromagnetic spectrum, you know that, right? Here. Chapter 8, electromagnetic waves. Here you have this electromagnetic spectrum. So what's an electromagnetic wave? It's a combination of electric and magnetic field. And this is the electromagnetic spectrum. Okay, here this is the visible light, where we can see that picture. Okay, so higher frequency is in the violet side. So frequency will increase in this direction. So the maximum frequency is gamma rays. X-ray is lower than that, and maximum wavelength is radio waves. Okay, so downwards wavelength is increasing. On the top, as you go top, the frequency is increasing. Okay, this is the electromagnetic spectrum. So you should know the sequence. Gamma ray frequency is more compared to X-ray, and then ultraviolet, visible, and then if you go for a longer wave, it will be infrared, microwave, radio wave, and television, this one, AM radio, and finally long radio waves. Okay, so you should know how to arrange this different waves in. Suppose they give you microwave, X-rays, and say ultraviolet. You should say which one has got more frequency, which one has got the least frequency, or which has got the maximum wavelength, and which has got the least wavelength. So basically, you should know the electromagnetic spectrum. So if this is the visible range, and let me take this as violet and this is red. Okay, so frequency here is more because violet frequency is more. It is so in this direction, wavelength will increase, and in this direction, frequency will increase. Okay, because violet frequency is more compared to red. So here we have gamma rays. Next is X-rays. Okay, here will be UV. Is there anything in between? On this side, here the maximum wavelength will be radio. Here we have infrared and then microwave. Okay, at least these main things you have to remember. And some further radio waves, short radios, long radio waves, X-rays, ultraviolet. Yeah. So you should know the sequence of the increase in frequency. So you should know that X-ray frequency is more compared to say microwaves, and wavelength of infrared is more than violet. So this sequence you should know. And speed of light in vacuum is how much? C is 3 into
10 to the power 9.
8 meter per second. This is for visible light. Okay. What is C for X-ray? X-ray frequency is more, right? So is this more than 3 or less than 3? It is same. Okay. So even velocity of radio waves, it is same C. Okay. So any electromagnetic wave has got the same speed or velocity, just 3 into 10⁸, but the velocity will change with respect to medium. This C is in vacuum, which is 1 by square root of mu naught epsilon. If the medium has got some different mu and epsilon, then the C in the medium will be 1 by square root of mu epsilon. Is it clear? C does not depend on the whether it's X-ray or infrared. It is same for everything. Any electromagnetic wave will have the same C. Okay, but C will change from medium to medium. For air or vacuum, it is 1 by mu naught epsilon naught, which is equal to 3 into 10⁸. Okay, if the medium changes, then it will change. right? So frequency is changing. Okay, so since C is same for everything, that's also true, right? C is same, so C is nu to lambda. So if nu is increasing means lambda has to decrease, so the product is same. So for gamma rays, nu is more. So lambda for gamma ray should be less. So the product is always C. Got it? Nu for gamma rays is greater than nu of X-ray because X-rays are higher frequency. Okay, so that means that lambda for gamma ray should be less than lambda for X-ray, so that the product of nu into lambda is the same C. Is that clear? Yes?
Yes, sir. Yes, sir.
Okay. So the C is a velocity of electromagnetic wave. Doesn't matter whether it's light or X-ray or gamma ray radio wave. It's always same. So the frequency increases as we move towards left, the wavelength will decrease. So the maximum wavelength is towards right, whose frequency is least. So on the left side, the frequency is more, so the wavelength is short. On this side, the wavelength is short, frequency is high. On the right side, the wavelength is more, the frequency is less. So that the product of nu to lambda is always C. So electromagnetic spectrum, you should know how to arrange the different variation in the sequence of increasing wavelength or increasing frequency. Electromagnetic wave direction. Okay. So what's an electromagnetic wave? What is electromagnetic wave? It's combination of
electric field and magnetic
Yeah.
field.
E and B, and it's a special combination like electric field B, or I can say electric field and magnetic field are perpendicular direction, and the direction of propagation of the wave, the direction of the wave that we represent as wave cap, it's equal to E cap cross B cap. Electric field is a vector, right? It have a direction. Even magnetic field is a vector, so it have a direction. Okay, and the direction of propagation of wave is given as the direction of E cross B. See, this is the variation of electric field. Electric field is in the x direction. X-axis upwards, y-axis out of the plane of this paper, z-axis is towards right. Okay, so electric field is towards, in this particular case, they are taken in the direction of x-axis. So it's vertically upwards, here is downwards. So basically in the direction of x-axis. And once you have electric field like this, magnetic field should be along the y-axis, perpendicular to this one. So it's along the y-axis. Okay, and the direction of propagation of wave is given as E cross B. So E is along I cap, B is along J cap. So what is I cap cross J cap? It is K cap, right? So K cap is the direction of Z axis, which is towards it. So this wave is propagating towards the right direction. So this is how electromagnetic wave will look. Both E and B are in phase, but the directions are 90 degrees. And the direction of propagation of wave is 90 degrees to both electric and magnetic field. There is the relation between. And what is electromagnetic wave? They are solution of which equations? Electromagnetic waves, which is this one, is solution of which set of equations? It is solution of these equations. Okay, we have Maxwell equation, right? Basically, it gives electric field and magnetic field relation. Okay, so in this set of four equations, if I put this value of E as this one, E equal to E naught into sine omega s kx minus omega t, and B as B naught sine kx minus omega t, it will solve these equations. So electromagnetic solution of this set of four equations, and that solution will have this particular property. Electric field being one direction and magnetic field in perpendicular direction, and the direction of the propagation of the wave is given as E cross B. Okay. So both electrical magnetic have the same. If it is sine kz minus omega t, magnetic is also sine kx minus omega. This will be same variation, same phase. There is no phase difference. Only the amplitudes can be different. Amplitude can be E naught and this can be B naught. And what is the relation between E naught and P naught? They are also related. It cannot be arbitrary. What is the relation? For an electromagnetic wave, E naught and B naught are related. What is the relation between these two? It's related to C.
So C equal to E naught by B naught.
So first you learn electric field and then you learn magnetic field. So you can remember that way. C is E naught by B naught. Okay. So once I have, so suppose in a problem, if I say B of the electromagnetic wave is say phi sine omega is say 2t minus kz, right? So k is say some 3 into z. So this is say E1. So once I have this, see, once I look at this one, I should know this is a wave traveling in z direction. This is a wave traveling in z direction because as time increases, z will increase for the phase to remain constant. Okay, so once I have this variation, this I told in the class itself, if you have a function like this, f of x minus a, which is same as, see, this is f of x. F of x minus a is f of x shifted towards right by a. So this is x minus a. Okay, but since I have this a into t, so as time increases, this thing will keep on moving towards right. Okay, so this is a wave traveling in the x direction. Okay, this is a wave traveling in x direction. Similarly, here f as a function of z minus at. This is a wave traveling in z direction. Got it? No. So this function can be a sine function. So this is a wave traveling in z direction. Suppose this was ky minus omega t, then this is a wave traveling in y direction. If it is kx minus omega t, it's a wave traveling in the x direction. So since they are given as z minus omega t, this is a wave traveling in the z direction. So direction of wave is z. And since in this particular problem, we are given this as 3z. So I know that the direction of the wave is z cap. Okay, and direction of B is j cap. B cap is j cap. So E cap can be I cap because E cross B should give me z. So I cross j is z. Yeah, so E is around I cap. So E is E naught into, should be the same function. If B is phi into sine whatever this thing, so it should be E naught should be the same sine into this one, sine omega, this same thing. Okay, and what about E naught? E naught should be, because C is E naught by B naught, and B naught is phi. So E naught is phi into C. So this E naught is phi into C. Okay, so you got the question. Suppose if I give By as this one, looking at this P and Z combination, I can immediately conclude with the direction of propagation of the wave is Z direction. And since they are given as By, the magnetic field direction is Y. Okay, from there I get the conclusion that the electric field direction should be I cap, because direction of propagation of wave direction is E cross B. The direction of propagation of the wave is E cross B. Okay, since this wave direction is Z cap and B direction is Y cap, so this E should be X cap because X cross Y is Z cap. So from this I get the conclusion that the electric field around this one, and the time variation or this one should be same for both electric and magnetic. This is the property in the solution of the electromagnetic wave. right? Both should be in phase. Okay, but E naught and V naught are related by this relation. C is E naught by V naught. Okay, so from this I get this expression for electric field as phi times phi into C. So this E naught is phi into C. Okay, into this function. So this relation, you know, C is E by B. So some more is a transformer. This already little bit is there. So should I continue or should I do it tomorrow?
Anything, sir.
Huh? Ritu is there, Ritu is not there. Nitish,
Sir, only 7 are there, sir.
yeah, should I continue?
Sir,
Yes.
your wish, sir.
Okay, we'll continue. And I'll repeat
Your
Okay.
wish.
what is there. Karthikeyan is there.
Yes, sir.
Okay, it'll cut in 7 more minutes. I'll continue. And I'll rejoin again. Okay, so you got this
Okay.
relation between C and B. C is nothing but E by B. And this electromagnetic wave has got the property that both if electric field is in X direction, magnetic field should be in Y direction. And the wave propagation will be in the direction of E cross B. Okay, so if I complicate it, suppose I say, let me do it here. Let me complicate it a little bit. Suppose I say magnetic field is in the X direction, which is say some B naught into, and the direction of propagation of wave is, let me complicate it further. Let me take the direction of propagation of wave as Y direction. So then it should be sine K Y minus omega t. So once I know the magnetic field of this electromagnetic wave is this one. So first thing I can conclude is the direction of propagation of wave.
Y direction, sir.
So direction of wave, propagation of wave is Y direction. Okay, and the magnetic field direction is I cap or X cap. Okay, so from this I can find the direction of the E. It's either J cap or minus J cap. That you have to figure out. So E cross B, if it is J, okay, J cross I is I cross J is K. So J cross I is minus K. Okay, so direction of propagation. Hold on, E is not J because propagation of the wave is J. So E is either K cap or minus K cap. It should be either K cap or minus K cap. Is it clear? Because wave I have taken as Y direction. Okay, and magnetic field is I cap because it's X component. So magnetic field direction is I cap. So electric field direction will be the other one, which is Z direction, which is either K or minus K. So K cap plus I cap is, and then J cap. So K cross I is J. So yeah, this is correct, right? So this one is correct. So electric field direction is plus I cap, sorry, plus K cap. Is that clear?
Okay, sir.
I just complicated it. I made direction of propagation of wave as Y, okay, and B direction is I cap because X component is given. From that I can find the direction of the propagation of this one as okay. If I complicate it a little bit further, just a minute. Suppose I make this thing as plus Y, okay, then this means the direction of propagation of wave is, what is the direction of the wave? Anyone?
Y only, no, sir.
Minus Y cap. Because f of x minus a is f of x shifted towards right by a, but f of x plus a where A is positive, okay, it's f of x shifted towards left. So this is a wave, suppose this is at, so this will be a wave
Okay,
minus x direction.
okay, sir.
Okay, just to complicate, I'm doing that, but here they are taken only minus, right? So if it is minus means it's traveling the positive z direction. Okay, suppose this was k z plus omega t, then it's traveling the minus z direction.
Okay, sir.
Okay. See, basically this whatever this argument should be constant, right? X plus omega at should be same. So as time increases, okay, x should decrease. As time increases, x should decrease for this combination to be same. So this is the wave traveling the negative x direction. But suppose this is x minus at, for this to be same, as time increases, x should increase. So this means that this is a wave traveling the positive x direction. Okay, so this is a wave traveling the minus y direction, and b is along x direction, so I cap, wave is along minus k cap. So electric field direction should be either k cap or minus k cap. Okay, so k cross I is j. Okay, but we want minus j. So it's not this one, so it should be this one, and minus k cross I is minus j. Because I can forget this minus, just take this one, k cross I. K cross I is j because you're taking cyclic order. I, j, I, j, k. Okay, so I cross j is k, j cross k is I, and k cross I is j. Okay, so k cross I is j, but here you want minus j. Okay, should be minus k. Minus I can keep it outside, and k cross I is j, and this minus thing, so it should be minus k. So this is the way electric field is in the minus z direction. So this is the direction of magnetic field, and suppose z axis is this is x axis, right? So this is y axis, okay, and the wave is traveling downwards, and x, y, this is y axis, and z axis outwards. So electric field is in this direction, and the wave is traveling downwards. Okay. So the basic thing is, looking at this argument, I can get the direction of propagation of the wave. Okay, and since this is given as Ex, the direction of the wave, electric field is I cap. From there, I can get the direction of magnetic field as J cap. Is it clear?
Yes, sir.
Yes, sir.
Okay. Electromagnetic wave direction and E and B direction of wave propagation.